Okay, so now let's use this dilution equation in a problem. So dilutions is a technique that's pretty much required in every clinical science laboratory or any like maybe drug testing, environmental labs, or analytical labs where you're testing samples maybe from lakes, trying to test the pH, or testing all sorts of all kinds of different possibilities here. These skills you learn in the lab will serve everyone well, and if you look into a position of being a lab technician, I there's nothing really that's there's really no disadvantages. It's a great I think it's a great position to have, and learning these skills will serve everyone well. Looking to pursue maybe a field, pursue a career in the field of science. So I totally recommend if students want to go down that path, maybe testing out chemistry, seeing if chemistry is right for you, definitely something to consider. Okay. So let's describe how we would prepare 2.50 liters of a 0.360 molar solution of sulfuric acid, starting with concentrated sulfuric acid that is 18.0 molar. Okay, so looking at our picture here, we see that we want to figure out what volume of 18 molar sulfuric acid will give us a diluted solution of 0.360 molar H2SO4 that is 2.50 liters. Okay. All right, so this was the volume and concentration of our dilute solution, and the one on the right was the one on the left is what we is the solution we considered in the previous exercise. Okay, so first let's calculate the moles of that we need in our desired solution. Okay, so one thing we could do is we could first say, okay, we need the M1 V1 equation. M1 times V1 equals M2 times V2. Okay? So in this case, so I won't use this equation yet. I'll go back to this. Okay? So first, we want to calculate the moles that we need in our desired solution. So we're going to rearrange our molarity equation. So molarity equals moles over volume to read moles. So moles, we'll solve for moles, equals molarity times volume. Okay? So we know we have 0.360 mole per liter. So I write it as mole per liter, so the unit, the units would cancel out. And then we're going to have 2.50 liters. So we want to figure out how many moles of that do we need in this solution. So we multiply the molarity by the volume of our desired solution here. And we get 0.900 mole H2SO4. Okay? So now we're going to ask ourselves, what volume of concentrated H2SO4 would contain the same number of moles of H2SO4? So we're going to recall that equation, mass times volume equals N again. Okay. Now let's solve for the equation for the volume of the solution. So we know that molarity equals M over V. Sorry, N over V. All right, so now we know molarity. We know the molarity we want, right? Because we know the molarity of concentrated sulfuric acid is 18 molar, so M equals 18.0 molar. And then the amount of moles we want in our final solution is 0.90 moles, right? So we just figured that out in the previous step. So we're going to solve for V. So we're going to solve for V, right? So we rearrange the equation. And then V times M equals N. And then if we isolate M, to isolate V, we get N over M. Okay, let me just clean this up a little bit. Okay, so our volume would equal 0.900 moles per 18.0 moles per liter. Okay, so if we do that, our moles will cancel and we're left with liters. So what we get is 0.0500 liters, or in this case, 50 milliliters. Okay, so let's answer this question now. We can prepare 2.50 liters of a 0.360 molar H2SO4 solution by adding 50.0 milliliters of concentrated sulfuric acid to enough water to give a total volume of 2.50 liters. So we never add the other way around. Always so always adding the acid to water. Never, remember AA, add acid to water, never add water to the acid. Okay? Alright, so that's how we would solve a dilution equation. Now let's go back to the M1V1 equation. We can definitely do this as well with the M1V1 equation. So let's revisit that. So this is only for dilution. So only for dilutions. So never for anything else. Okay? So M1 is what our original concentration is. So we're starting out with 18 molar. So that's 18.0 molar. We need to take a volume of that solution to get to our new solution. So we don't know V1. So V1 is what we're solving for, okay? M2 is our diluted solution, and that's going to be 0.360 molar. And then our volume of the diluted solution is known, and that's 2.50 liters, okay? So if we rearrange the M1V1 equation, so we would get V1 equals M2 times V2 over V1. Okay, so we can represent this as a factor of volume, that our molarity is going to either it won't never increase, but it'll decrease by the factor of the volumes. Okay, so in this case we have 0.360 molar times V2, which is, oh sorry, I meant this the other way around. I meant the ratios of the molarities will be influenced by the will be a factor for the volume. Okay, like that. So the ratio of the molarities will give us the volume we need to get a diluted solution to a new volume. All right. So M2 here, 0.360 molar divided by 18.0 molar times 2.50 liters. Okay. So if we do that, if we set that equal to there, we get we will get essentially what we had before, what we did down below in the stepwise, in the stepwise calculations, and in this case v2 will or in this case right. So we v1, sorry, not v2, v1 will equal 0.0500 liters. Okay. So in this equation, M1, V1, M2, V2, typically you should use M2, V2 as your diluted solution, and then M1, V1 should represent your undiluted solution. But honestly, it doesn't really matter. But for just like clarity, you should just think like M1, V1, that's your undiluted solution. M2, V2, that refers to your diluted solution. But it does not really matter because you get the same answer regardless if you switch the values on one side of the equation. Okay? But obviously don't intermix the values, right? Don't pair M1 with V2. That's not the equation. Okay. So now let's try another example here. Oh, okay. So now we're getting into, now we're moving on to what we call solution stoichiometry. Okay. So there'll be lots more examples of dilution equations, of using this dilution equation on the practice problems I posted on Canvas. So there'll be more practice with that, and we'll definitely have more practice in discussion. All right, so let's move on now to something we call solution stoichiometry. So this is, so if students struggled with regular stoichiometry, they will definitely struggle with solution stoichiometry. So it's best to kind of get the hang of stoichiometry by just doing lots of problems. So lots of problems until you master the concept. Okay? So a common way of conducting chemical reactions is pretty much using reactive reagents in dilute form. So usually when we dissolve something in solution, they're less reactive because they're surrounded by solvent molecules. So since our molarity calculations, they include the unit of moles, we can actually use the concentration of a reagent and a chemical reaction to do stoichiometry equations. So we can actually determine the amount of something that's consumed or formed based on the molarity of a solution. Because with molarity, we can find how many moles was used in the chemical reaction, and we can figure out like how much of a particular chemical was present in a sample. So that's one of the key advantages of titrations. They're very accurate in determining the amount of substance in, like, say, a commercial sample. Okay. So let's just get started here. The reaction between oxalic acid and sodium hydroxide can be described by this following equation. So we have oxalic acid here reacting with sodium hydroxide. So that's what we call an acid-base reaction. So we'll go over chemical reactions in the next lecture. We'll go over a number of different types of reactions that happen in aqueous solution, and we'll actually be doing a experiment exploring these reactions. So that will be fun. So H2C2O4, oxalic acid. If you don't know what oxalic acid is, it's found in certain plants. One common source of oxalic acid is in spinach. So if you eat too much spinach, you may feel sick, and that's because it's oxalic acid. And the thing about oxalic acid, if you eat too high of a diet of oxalic acid, you will develop kidney stones. So kidney stones is the deposit from things with too much oxalic acid, so the calcium in your body will actually form a mass that can't be filtered through the kidneys, and the oxalic acid salt with calcium, so calcium oxalate, that is what gives rise to kidney stones. And if anyone knows anyone with kidney stones, they can be quite painful, and that's because they are pretty much substances that should not be in your body because they are salts. They are probably particularly large if they aggregate, and they're solids, so they're kind of very dense. So oxalic acid, although it's an acid, it's salt oxalate. When paired with calcium, not very soluble, so it can't be filtered out easily through the body. Anyway, so we're going to use this chemical reaction. See, here is an acid base. We get sodium ion, oxalate ion, and water as our byproducts. So there's a lot of information here, so we're going to break it down step by step. Calculate the concentration of an oxalic acid solution if it takes 34.0 milliliters of a 0.2 molar sodium hydroxide solution to consume the acid in a 25.0 milliliter sample of the oxalic acid. Okay, so first thing students will probably think about doing is using the dilution equation. Well, that doesn't make sense because you have two different solutions here. So we're going to throw that out the window. So don't use the dilution equation when you're given a chemical reaction. Okay? So a dilution equation should always be when you're given one substance and you're trying to dilute it from a higher concentration. All right? So let's write what we're given here. So we're given the volume of oxalic acid, which is 25 mils. We're given the molarity of sodium hydroxide, that's 0.2 molar, and the volume of sodium hydroxide, which is 34 milliliters. Now we need to figure out the molarity of oxalic acid, okay? So you see here, you may think, oh, we have all the variables for M1V1 equals M2V2, but we can't use that equation. It wouldn't make sense in this particular instance. Okay, so this picture on the right is a apparatus here. This is what we call a titration. So a burette has your what we call the titrant. So a titration is a technique in chemistry where you use the concentration of one substance or the titrant to determine the concentration of the analyte or analyte, or the substance where you don't know the concentration, but you have a sample size, or you may know the concentration. Actually, no, it's always you're trying to determine the concentration of whatever's in solution. So it's usually a 25 mil. So it's usually a solution of unknown concentration. Okay. All right, so first things first, the chemical equation here is pretty complicated. So let's rewrite it to simplify it, okay? So let's rewrite the chemical equation. So we have H2 C2O2 aqueous. So we're going to first rewrite, so oxalic acid is a weak acid, so we're going to keep it on the left side undissociated, okay? So that means it doesn't form ions because it's a weak acid. Sodium hydroxide, however, is a very strong electrolyte, so we can write it as sodium plus and OH minus when it dissolves in water. So we write plus sodium ion plus OH ion. So we had to put 2 in front of the sodium and the hydroxide because there's 2 of them there's a coefficient 2 in the original chemical equation. So acid-base reactions, usually when you have a strong acid, strong base, it goes in one direction and you get 2 sodium plus C2O2 2 minus So I'm going to write the symbols underneath here because I'm running out of room. Plus 2H2O. So you see here, we formed water in this equation. That's because the OH groups here, they react with the 2 hydrogens here, and that gives us 2 water molecules. So that's an acid-base reaction. Hydroxide is a strong base, will react with anything acidic, anything weakly acidic, and that's usually it'll react with acids. So carboxylic acids reacts very fast. Nitric acid, sulfuric acid, hydrochloric acid, very fast. So the chemical really has to have an acid in its name for hydroxide to react, because compounds can be classified acids, but usually a true acid is when we name it as a typical acid because it forms relatively low pH solutions or very acidic solutions. Okay, so now since 2 sodium appears on both sides of the equations, we can simplify this equation because they cancel out, right? Because they are spectator ions, they are actually not doing anything in the reaction, they are just part of the solution. Okay, so now we can simplify this to H2C2O2 aqueous plus 2OH minus, so 2 hydroxide ions, to give us oxalate, C2O2, 2 minus, plus 2 water molecules. And we look at our chemical equation, that is correct. Okay, here we go. So you could always simplify it. You don't have to though, but it helps to simplify it so you know the net ionic equation, which is the equation that tells you what type of what's happening in the reaction, what chemical change is occurring. Okay. So since we know the volume and concentration of the sodium hydroxide solution, it seems reasonable to start here and calculate the moles. Okay, so we'll stop here and we'll finish up this problem in the next video, and that'll probably be the end of this lecture. I might actually go over one more dilution problem just so students have additional example to refer to. Okay, so see everyone in the next video.